Welcome to the deep dive.
There's that feeling, right? Part excitement, part maybe sheer terror when you see system design interview pop up on your calendar.
Oh yeah, definitely felt that one myself.
It's just not like your standard coding interview, is it? You're not just recalling syntax or, optimizing a loop.
Not at all.
This is different. It's about thinking on your feet, under pressure, trying to visualize this massive system from nothing.
And then explaining it clearly.
Exactly. Explaining it clearly. It feels intimidating because it's not just testing what you know, but really how you think about complex problems.
It absolutely is. And that's the key thing interviewers are looking for, I think. It's less about having the perfect answer memorized, because often there isn't one single right answer.
Right.
It's much more about showing that you have a structured way to approach these big kind of ambiguous problems.
Yeah.
It really is a different beast in the whole interview game. Yeah, and that's exactly why we're diving deep today. Our mission, really, for you listening, is to help cut through some of that daunting prep work. We've looked at a whole bunch of resources, especially drawing from like an insider's guide and expert advice, and we're trying to boil it all down into something really actionable.
Something you can actually use.
Yes, not just theory, but things that lead to those aha moments.
Yeah.
Where you suddenly see how the pieces fit together and hopefully turn that dread into, well, maybe even a bit of confidence.
That's the goal. Think of this as your guided tour. We're going to walk through the fundamental building blocks, the core ideas behind scalable systems.
Okay.
We'll unpack some of the complexities you might not see at first glance, and then give you a solid framework, a kind of roadmap for tackling pretty much any system design question they throw at you.
So by the end of this, the idea is you'll feel, equipped, ready to face it.
Yeah, equipped and hopefully empowered, ready to actually have that conversation in the interview.
Okay, let's get into it. Before we can even think about designing, the next Facebook or Netflix or whatever, we've got to understand the absolute basics, like the journey of just one single request. What actually happens, technically, when you type, say, api.mysite.com into your browser?
Right. It seems so simple, but it's the foundation for everything else. It all starts there.
It really does.
So you type that domain name.
Huh.
The very first thing your browser, or maybe your mobile app does, is it has to figure out where api.mysite.com actually lives on the internet. It does that by talking to the domain name system, or DNS.
The internet's phone book.
Pretty much. And usually this isn't something you run yourself. It's typically a paid third-party service. Its job is just translation. Turn that human-friendly name into an IP address. Those dotted numbers like 15.125.23.214.
Got it. So DNS gives you the actual address. Then what?
Okay, once your browser has that IP address, it knows where to send the request. So it opens a connection and sends an HTTP request hypertext transfer protocol directly to the web server sitting at that IP address.
And the server sends something back.
Exactly. The web server processes the request and sends back a response. If you're browsing a website, that's typically an HTML page. If it's an app talking to an API, it's usually a JSON response.
JSON. Right, that lightweight data format.
Yeah, JavaScript object notation. Super common for APIs because it's easy for machines to parse and pretty readable for humans too. It just sends the data the app needs, ready for the app to display or use.
Okay, so that's the life of one request. Browser asks DNS, gets IP, asks server IP. Server sends back HTML or JSON. Simple enough. But where does all this traffic come from? Does it matter if it's a website versus a mobile app?
It does matter. In terms of how the backend might be structured, you basically have two main sources: web applications and mobile applications.
Okay.
For a web application, you typically have server-side code, maybe written in Java, Python, Ruby, Node.js, whatever, doing the heavy lifting. That's the business logic, talking to databases, storing stuff.
Right.
Then you have the client-side code, HTML, CSS, JavaScript running in the user's browser, handling how things look and feel, the presentation layer.
Makes sense. And mobile apps, they don't run HTML in the same way.
Correct. Mobile apps use the same underlying HTTP protocol to talk to the server, but they usually expect JSON data back. They have their own native UI component, so they just need the raw data from the server to populate their screens. Like, fetch user profile, get back JSON with name, email, etc.
I see.
And what's really key here, and what you need to remember for interviews, is that this simple flow, it's the bedrock. Everything complex we build later, load balancers, caches, databases, it all sits on top of this basic request response cycle. Understanding this baseline is crucial.
Okay, so we start simple. One server may be doing everything, web serving, database, the whole shebang. But obviously that doesn't last long if your app gets popular. What's the first big step when that single server starts to choke?
Yeah, you hit the limits fast. The very first, almost mandatory step is tier separation. You need to split your web application tier from your data tier, meaning your web servers are just handling the incoming requests and running the application code. They don't store the persistent data anymore. That job goes to dedicated database servers.
Okay, so they become specialized.
Exactly. This is huge because now you can scale them independently. If you get more web traffic, add more web servers. If your database is working hard, you focus on scaling the database side. It stops one tier from dragging the other down.
That makes a ton of sense. But okay, now you have multiple web servers potentially. How do you manage traffic going to them? You can't just give users a list of IPs.
Right.
And what if one server fails?
Precisely the problem. This introduces the need for a load balancer.
Right. The traffic cop.
Kind of, yeah. Its main job is twofold. First, it eliminates the web tier as a single point of failure, SPOF. If one web server dies, the load balancer just stops sending traffic there and directs it to the healthy ones. Users ideally never notice.
Okay, crucial for uptime.
Absolutely.
Really?
Second, it distributes the load. If you have way more requests than one server can handle, the load balancer spreads the incoming traffic evenly across all the web servers in its pool. This prevents any single server from getting overloaded, which keeps responses fast.
Does it do anything else? Like for security?
It does, actually. A common setup is that users connect to the load balancer's public IP address. But the web servers themselves, they often sit on a private network with private IPs.
So they're not directly exposed to the internet.
Exactly. They only talk to the load balancer, which acts as a gateway. This shields them from direct attacks, adding a nice layer of security. So the benefits are clear. Better availability through failover, and easy scalability. Just add more web servers to the pool behind the balancer as needed.
Okay, web tier sorted, load balanced, reasonably secure.
Yeah.
Now, back to that data tier we separated. All these web servers need to talk to a database, but which kind? This feels like a massive decision point. SQL versus NoSQL.
It really is. And it's less about which one is better and more about which one is the right tool for your specific job. It comes down to your data structure and your consistency needs.
Okay, break that down. SQL first, the traditional choice.
Yeah, relational databases, RDBMS, using SQL. Think MySQL, PostgreSQL, Oracle SQL Server. They store data in tables with rows and columns, enforcing a predefined schema.
Very structured.
Very structured. And their superpower is join operations using SQL. You can easily combine data from multiple tables with strong consistency guarantees, usually A-side compliance. If your data has complex relationships and you need transactions like banking, e-commerce SQL is often the default proven choice. It's been the workhorse for decades.
But then everyone talks about web scale and NoSQL. When does that make sense?
You typically look at NoSQL databases like Cassandra, MongoDB, DynamoDB, Redis, when the rigid structure or the scaling limitations of a single relational database become a problem. Maybe you have absolutely massive amounts of data or incredibly high traffic, or your data doesn't fit neatly into tables.
Like user profiles with varying field or censored data.
Exactly. NoSQL databases come in different flavors. Key value stores, document stores, column stores, graph databases, each optimized for different patterns. The big trade-off is they generally don't support joins as easily or efficiently as SQL databases, and they often offer eventual consistency rather than strict ASID compliance.
So it's a deliberate choice based on scale, data shape, and consistency needs.
Precisely. You don't just jump to NoSQL because it's trendy. You evaluate if the relational model is genuinely holding you back for your specific use case.
Okay, decision made, we picked our database type, but like the web tier, having just one database server is risky. If that goes down, game over.
Big time. That's why data replication is essential for the data tier's high availability. The most common pattern here is the master-slave model.
Master-slave, okay, how does that work?
You have one master database. This is the only one that handles write operations, inserts, updates, deletes. It's the single source of truth.
Yeah.
Then you have one or more slave databases. These databases replicate all the data changes from the master, usually asynchronously. Their main job is to handle read operations.
So you split the workload, writes go to master, reads go to slaves.
Exactly. This takes a huge load off the master, allowing it to focus on writes, and you can scale read capacity simply by adding more slaves.
Smart. What happens if one fails? Say, a slave goes offline.
If a slave goes offline, it's usually not catastrophic. Read traffic just gets redirected to the other slaves, or maybe temporarily to the master if needed. You then work on bringing up a new slave to replace the failed one, which starts replicating from the master again.
Okay, manageable. But what if the master fails? That sounds bad.
That is the more critical scenario. If the master fails, you need a failover process. Typically, one of the existing slaves is promoted to become the new master. All the application traffic, reads and writes, is then directed to this newly promoted master.
And then you add a new slave.
Yep. You provision a new slave that replicates from the new master to restore the replication setup. The tricky part during master promotion is often dealing with replication lag.
Lag, meaning the slave wasn't perfectly up to date.
Right. Replication is often asynchronous, so the slave might be a few milliseconds or sometimes even seconds behind the master. When the master dies, the slave being promoted might be missing the last few committed transactions.
Ouch. So you might lose data.
You might. Or you have to make a choice. Accept potential data loss for faster failover, or pause writes and run complex recovery scripts to try and reconcile the data, which increases downtime. It's a tough operational challenge. That's why things like synchronous replication or consensus protocols like Paxos or Raft exist for more critical systems, but they add complexity.
You mentioned multi-master briefly. Why is that more complex? Sounds good to write anywhere.
It sounds great for availability, yeah. Writes can go to any master,
Right.
but it introduces write conflicts. What happens if two users update the same record on two different masters at basically the same time?
Which one wins?
Exactly. Resolving those conflicts automatically is incredibly hard and can lead to data inconsistencies if not handled perfectly. Master-slave avoids this entirely by having only one place for writes. That simplicity is often worth the trade-off.
Makes sense. Okay, so we've got load balancing for web traffic, replication for database availability, but we still need speed, right? Users hate waiting. How do we accelerate things?
Right. Performance is key. This brings us to three crucial techniques. Caching, using content delivery networks, CDNs, and designing a stateless web tier.
Okay, caching. Everyone sort of knows what a cache is, but in system design, it's more strategic than just your browser history, right?
Absolutely. Think of a cache as a high-speed, temporary data store, usually kept in memory, RAM, which is much faster than disk or network access. Its purpose is to store the results of expensive operations like complex database queries or calls to external services or data that's accessed very frequently.
So you compute it once, store it in the cache.
And the next time you need it, you grab it from the super fast cache instead of doing the slow operation again. The benefits are huge. Your application feels much faster. You drastically reduce the load on your database or backend services, and you can often scale the cache layer independently.
But caches have limited size. What happens when they fill up? How does it decide what to kick out? And where do these caches even live?
These questions. When a cache is full, you need an eviction policy. The most common one is least recently used, LRU. Kick out the data that hasn't been touched in the longest time.
Yeah.
Others exist, like LFU, least frequently used, or FIFO, first in, first out, used for different access patterns.
Yep.
As for where caches live, they can be anywhere. Client-side in the browser, intermediary caches in CDNs, which we'll get to, or dedicated server-side distributed caches like Redis or Memcached. These are shared in-memory stores that multiple web servers can access. Managing what to cache and how long to cache it, cache invalidation, is also a critical design decision to avoid serving stale data.
Got it. Okay, next speed booster. CDNs, content delivery networks. These always feel a bit like magic when a website based in, say, California loads instantly here. How do they actually work?
They kind of are magic. A CDN is essentially a network of servers distributed all around the globe. Their specialty is storing and delivering static content, things like images, videos, CSS style sheets, JavaScript files, basically anything that doesn't change frequently per user.
So they keep copies everywhere.
Pretty much. The core idea is geographical proximity. When a user in London requests an image from your website hosted in California, instead of fetching it all the way across the Atlantic, their request gets routed to the nearest CDN edge server, maybe one also in London or nearby in Europe.
And if that edge server has the image?
It serves it directly, super fast. If it doesn't have it cached yet, the CDN edge server will fetch it from your origin server, your main web server, store a copy locally in its cache, usually respecting a time to live or TTL you set, and then serve it to the user. Subsequent users nearby will get the cached copy.
So CDNs aren't just about speed, they also take a massive load off your origin servers for all that static stuff.
Exactly. Huge reduction in bandwidth costs and load on your core infrastructure.
Yeah.
It lets your servers focus on the dynamic, personalized content, but they're not a cure-all.
Right. What are the catches?
Well, cost is one. CDNs are usually paid services. You need to set the TTL appropriately. Too long, users get stale content. Too short, you lose the benefit. You need a fallback if the CDN has issues. And cache invalidation can be tricky. How do you force the CDN to update a file before the TTL expires if you change it? Usually via APIs or versioning file names, image.png.v2. And crucially, CDNs are primarily for static or semi-static content. Highly dynamic, personalized data still needs to come from your origin.
Makes sense. Okay, the third accelerator, stateless web tier. This sounds philosophical. How can a web server be stateless? Doesn't need to remember who the user is?
It sounds counterintuitive at first, yeah. A stateful server does remember things about the user from one request to the next, maybe their session ID, what's in their shopping cart, stuff like that, often stored right there in the server's memory.
Okay, seems convenient. What's the problem?
The problem is scaling horizontally. If you have stateful servers and use a load balancer, user A's first request might go to server 1, which stores their session, but their next request might go to server 2, which has no idea who user A is. Their session is lost, their cart is empty, nightmare. It also makes adding or removing servers really hard.
Ah, I see. So stateless means the server doesn't store that user's specific stuff locally.
Exactly. The solution is to move all that state user sessions, temporary data, out of the individual web servers and into a separate shared storage layer. This could be your main database, a NoSQL store, or very commonly, a dedicated distributed cache like Redis or Memcached.
So now any web server can handle any request from any user.
Precisely. The web server receives a request, maybe fetches the user's session data from the shared Redis store using a session token, processes the request, maybe updates the session in Redis, and sends the response. The server itself holds no per-user state between requests.
And the benefit is massive scalability.
Massive. It makes your web servers totally interchangeable, like worker bees. You can easily add or remove them based on load, auto-scaling without worrying about losing user state. It simplifies deployment, improves fault tolerance. It's pretty much fundamental for building large-scale web applications today.
Okay, we've built a system that's fast, scalable at the web and data tiers, highly available. But real-world systems often have many different parts that need to communicate. Maybe processing a photo upload, sending an email notification, updating analytics, doing all that synchronously while the user waits. Sounds bad.
It's often terrible for user experience and system resilience. If one small part of that synchronous chain fails, the whole request might fail. This is where asynchronous communication and message queues become vital.
Message queues. Yeah. Like a digital post office for different parts of the system.
That's a great analogy. A message queue, like Kafka, RabbitMQ, AWS SQS, acts as a buffer or intermediary between different services. One service, the producer or publisher, writes a message, basically a task description like process image 123 or send welcome email to user 4556 onto the queue. And then it immediately moves on. It's job done for now. Later, another service, the consumer or subscriber, connects to the queue, picks up that message, and performs the actual work described in it, resizing the image, sending the email.
Ah, so they're decoupled. The producer doesn't have to wait for the consumer or even know if the consumer is running right now.
Exactly. That decoupling is the primary benefit. It improves resilience. If the email service is down, messages just pile up in the queue until it comes back online. The main application isn't blocked. It enhances scalability. If the queue gets long, you just spin up more consumer instances to process the backlog faster. And it smooths out spikes of bursts of activity, creates messages, but consumers can process them at a steady pace.
Super useful for background tasks. Okay, final piece before we get into the interview specifics. Logging, metrics, and automation. Seems obvious, but why are these so non-negotiable at scale?
Because without them, you're flying blind. On a tiny site, maybe you can SSH into the server and look at logs. On a system with hundreds or thousands of servers. Impossible.
Right.
Logging is how you debug problems and understand what happened. You need structured logs aggregated into a centralized system like Splunk or an ELK stack so you can search, filter, and analyze them effectively, especially for tracing errors across multiple services.
And metrics. That's about performance.
Performance, health, and business insights. You need system-level metrics, CPU, memory, disk I/O on individual machines, aggregated metrics, database latency, cache hit rate, queue lengths for entire tiers, and critically, key business metrics, daily active users, signups, revenue. Metrics tell you how your system is performing and whether it's meeting its goals. You need dashboards and alerts based on these.
And automation ties it all together.
Pretty much. Automation reduces manual toil and human error. Continuous integration, CI, automatically builds and tests code on every commit, catching bugs early. Continuous delivery deployment, CD, automates the release process, letting you ship updates faster and more reliably. Infrastructure as code, IAC, automates provisioning servers. At scale, you automate everything you possibly can. These aren't just features, they are foundational practices for operating complex systems reliably.
We touched on database replication, master-slave, but sometimes even that's not enough. Maybe the right volume is too high for a single master, or the total data set is just too enormous to fit on one machine, even a big one. What are the next steps for database scaling?
Right, you hit limits even with replication. The two main paths forward are vertical scaling and horizontal scaling.
Okay, vertical first.
Vertical scaling means scaling up. You just make the single database server more powerful, add more CPU, more RAM, faster disks. You can get monstrously large database servers these days with terabytes of RAM. For some workloads, this can take you quite far. Simple conceptually, just buy a bigger box. What's the catch?
Several big catches. One, there's always a hardware limit you can't scale up indefinitely. Two, it significantly increases the risk of a single point of failure, SPOF. If that one giant, super expensive server goes down, your entire database is gone. And three, it gets prohibitively expensive. The cost per unit of performance skyrockets with those high-end machines compared to using commodity hardware.
So vertical scaling has its limits. That leads us to horizontal scaling, also known as sharding. This is where we spread the data across multiple machines.
Exactly. Sharding means partitioning your single logical database into many smaller, independent databases called shards. Each shard typically lives on its own server or cluster.
How does that work? Does each shard have the same tables?
Generally, yes. Each shard holds the same schema, the table structure, but it only contains a subset of the actual data rows. For instance, you might shard your users table across 16 shards, with each shard holding roughly 116th of the total users. Okay, but how does the application know which shard a specific user's data is on? If I want user 123, how do I find them?
That's determined by the sharding key, or partition key. It's one or more columns in your table whose value is used to decide which shard the data belongs to. A common method is to take a hash of the key, say hash userid, and then use the modulo operator. Sharded hash userid %, number of shards.
So userid 123 might hash to a value that, modulo 16, results in shard 5. So you query shard 5.
Precisely. Your application logic, or often a routing layer in front of the database, calculates the target shard based on the key and directs the query there. Choosing a good sharding key is critical for ensuring data is distributed evenly and avoiding hotspots.
Hotspots, like one shard getting way more traffic than others.
Exactly. Which brings us to the challenges of sharding. It's powerful, but complex. One challenge is resharding. What happens when your data grows and you need to add more shards? Or if data distribution becomes uneven?
You have to reshuffle everything.
Pretty much. You need to change your sharding logic, maybe go from 16 shards to 32, and then physically move potentially terabytes of data between servers. This is often a complex, risky online or offline operation.
Sounds painful. What other problems crop up?
The celebrity problem or hotspot key problem. Imagine sharding Twitter by userid. What happens when Katy Perry tweets? Her userid maps to one specific shard, and suddenly that shard gets hammered with reads and writes, while others are idle.
Right. The system is unbalanced. How do you fix that?
It might require complex solutions like identifying these hotkeys and maybe giving them their own dedicated shard or further subpartitioning just their data. Another big challenge is joins. Performing a SQL join across data that lives on different shards is usually very inefficient, if not impossible.
So how do people handle needing related data?
Often, they resort to denormalization. You might duplicate some data. For instance, if you need user profile information when displaying tweets, you might store the user's display name directly in the tweet record, even though it's duplicated from the user profile table. This avoids the cross-shard join when fetching tweets. It trades storage space and write complexity for read performance.
So sharding solves the scale problem, but introduces its own set of headaches. Resharding, hotspots, joins. You mentioned resharding involving moving lots of data. Is there a smarter way to handle adding or removing servers without that massive reshuffle?
Yes, thankfully. This is where consistent hashing comes into play. It's a specific hashing technique designed to minimize disruption when the number of servers or shards or cache nodes changes.
Okay, how does it differ from the simple hash key % approach?
That simple modulo approach is brittle. If you change n, the number of servers, from, say, 16 to 17, the result of hash key % in 17 will be different from hash key per 16 for almost every single key. This means nearly all your data needs to move, or your cache gets completely invalidated, the cache misses storm.
Right. Nightmare. How does consistent hashing avoid that?
Consistent hashing works by mapping both servers and keys onto an abstract hash ring, like a circle numbered from 0 to 232.1, or some large number. Servers are placed on the ring based on a hash of their ID or IP address. Keys are also placed on the ring based on a hash of their value.
Okay, everything's on the circle. How do you find which server owns a key?
You find the key's position on the ring, and then you travel clockwise around the ring until you hit the first server. That server is responsible for that key.
Ah, okay, so what happens when you add a new server?
This is the clever part. When you add a new server, say server D, between server A and server B on the ring, it only takes responsibility for the keys that fall on the ring between server A and itself, server D. The keys that were previously handled by server B but are clockwise from server D remain with server B. Only a small fraction of keys, those immediately counterclockwise to the new server, need to be redistributed.
Much less disruption. Same if you remove a server.
Exactly. If you remove server A, the keys it was responsible for now just naturally fall through to the next server clockwise, server D in our example. Again, only the keys managed by the removed server are affected. Everything else stays put. On average, only N keys need remapping when you add or remove a server.
That sounds way better.
Yeah.
Are there any downsides to the basic concept?
The basic approach can still lead to uneven load distribution. Servers might randomly land very close together on the ring, leaving one server responsible for a huge arc, many keys, and another with a tiny arc. You can also get unlucky with key hashes clustering.
So how do you ensure it's actually balanced in practice?
The standard solution is using virtual nodes, or replicas. Instead of placing each physical server on the ring just once, you place it multiple times using different hashes, e.g. hash server plus hashtag 1, hash server plus hashtag 2, etc.
So server A might appear as A1, A2, A3, scattered around the ring.
Exactly. Each physical server now becomes responsible for many small segments of the ring. As you increase the number of virtual nodes, the distribution of keys across the physical servers becomes statistically much, much more even. It smooths out the randomness. The trade-off is slightly more metadata to track, but the gain in load balancing and flexibility is usually well worth it. It makes adding and removing capacity much smoother.
Okay, this is brilliant stuff. We've covered the building blocks, scaling techniques, databases, caching, consistency. Now, let's pivot to the interview itself. You're sitting there, the interviewer says, design a system like Instagram's feed or design a URL shortener. It feels huge, maybe overwhelming. How do you even start? Is there a framework?
There absolutely is a framework, and following it is probably more important than knowing every single technology detail because, again, there's often no single right answer. The framework shows your process.
So it's about demonstrating how you think, how you collaborate.
Precisely. It shows you can break down a complex, ambiguous problem into manageable parts, make reasoned decisions, and discuss trade-offs. It's usually a 4-step process.
Okay, step 1. And I heard a cautionary tale about someone named Jimmy.
Step 1. Understand the problem and establish design scope. And yes, don't be Jimmy. Jimmy's the classic mistake. Hearing the question and immediately jumping to solutions, spewing out buzzwords like Kafka, microservices, sharding.
Okay. Bad move. Why?
Because you haven't understood the actual requirements yet, you must slow down, resist the urge to show off knowledge immediately, and ask clarifying questions. This is not trivia. You need to define the problem before you can solve it.
So what kind of questions should you ask for something broad like design a news feed?
You need to narrow it down. Ask things like, what are the core features? Just posting and viewing. Or also likes, comments, sharing, real-time updates. You can't build everything in 45 minutes. What's the scale we're designing for? How many users? Daily active? How many posts per day? This drives all your scaling decisions. Are there non-functional requirements, latency targets, consistency needs? Is eventual okay? Can users follow many people? Are there limits? Like the 5,000 friend limit on Facebook impacts design. What kind of content? Text only. Images, videos. This affects storage, CDNs, processing.
It's like being a requirements analyst first.
Exactly. You're gathering the specs for the system you're about to design. For that newsfeed example, maybe the interviewer clarifies. Okay, focus on 10 million DAU. Users can follow up to 5,000 others. Feed should include text, images, and video, and appear in reverse chronological order. Likes are important. Comments are out of scope for now.
Okay. Now you actually have something concrete to design. Your questions literally shape the problem.
They absolutely do. Skipping this step is probably the single biggest reason candidates fail system design interviews. It shows a lack of structured thinking.
Got it. Crucial first step. What's step 2 after you've clarified the scope?
Step 2 is to propose high-level design and get buy-in. Now that you understand the requirements, sketch out the main components and how they interact. Use a whiteboard or virtual equivalent.
Like drawing boxes and arrows.
Pretty much. Show the main services. Web servers, load balancers, databases, caches, maybe a message queue for asynchronous tasks. Talk about the data flow for key use cases. For the news feed. Okay, for feed publishing, a request hits the web server, we write the post to the database, maybe put a message on a queue for fan out. For feed reading, a request hits the server, we query a service that aggregates posts from followed users, maybe using a cache.
Should you define APIs or database schemas here?
Maybe briefly, if it helps clarify the interactions, but don't get bogged down in extreme detail yet. The goal here is to agree on the overall architecture with the interviewer. Walk them through it. Ask, does this high-level approach make sense? Are there any major components I'm missing based on their requirements?
So it's collaborative. Get their feedback early.
Absolutely collaborative. Get their buy-in on the main direction before you dive deep into any one component. Identify potential bottlenecks together. Maybe they'll say, okay, the feed aggregation sounds tricky, let's focus there. This ensures you're spending time on what they care about.
Okay, high-level design agreed upon. Now for step 3. This is the deep dive.
Exactly. Step 3 is design deep dive. Now you, often guided by the interviewer based on the high-level discussion, pick 1 or 2 key components and explore them in much more detail.
This is where we apply all that knowledge about databases, caches, etc.
Yes. How would you actually implement that feed aggregation service? What kind of database would you use and why? How would your schema look? How would you handle scaling? What are the trade-offs of your approach? Let's take an example component we discussed earlier, designing that unique ID generator.
Right, the Snowflake example. So
Yeah.
in the interview, you wouldn't just say use Snowflake.
No, definitely not. You'd start by reiterating the requirements. Okay, we need unique 64-bit numerical ID sortable by time, generating 10K secs. Then briefly discuss why simpler options don't work. Auto increment doesn't scale distributedly, UIDs aren't time-ordered, or 64-bit numeric ticket servers are SPOFs.
Setting the stage.
Exactly. Then you introduce the snowflake concept. So a common approach is to divide the 64 bits, then you'd break down the layout. 1-bit sign, always 0. 41 bits timestamp, milliseconds since epoch, gives 69 years, ensures time ordering. 5 bits data center ID allows 32 data centers, 5 bits machine ID, 32 machines per DC. 12-bit sequence number, resets every millisecond, allows 4096 ID as M's machine.
Explaining the why behind each part.
Yes. And calculating the capacity. 40096 ideasms, 1,000 Muellers, 32 machines, 32 data centers equals massive potential throughput, distributedly. Then you discuss trade-offs and considerations, clock skew, NTP, tuning bit lengths, high availability.
That connects it back perfectly. It shows you understand the principles and can deploy them. What about another example like the rate limiter?
Same process. Start with the why. We need a rate limiter to prevent DOS, control costs, avoid overload. Mention where it sits. Typically, server-side middleware returning HTTP 429. Then discuss algorithm trade-offs. Token bucket. Simple, allows bursts, but tricky tuning. Leaking bucket. Stable outflow, but bursts can block new requests. Sliding window log. Very accurate, but memory heavy. Sliding window counter. Good balance, memory efficient, slightly proximate, but often fine.
Comparing the options based on requirements.
Right. Then sketch the high-level architecture. Client, rate limiter, middleware. Check Redis counter, rate checked, 429, or forward API server plus increment counter. Discuss optimizations like multi-data center deployment, edge checking, and eventual consistency for the counters across regions. And finally, emphasize the need for monitoring its effectiveness.
So the deep dive is about showing detailed knowledge, reasoned choices, and awareness of trade-offs for specific components.
Exactly. You likely won't have time to deep dive into every component, so focus where the interviewer guides or where the core challenges lie.
Okay, makes sense. Then the final step, step 4, wrap up. What's crucial here?
The wrap-up is your final chance to consolidate and impress. First, identify bottlenecks and potential improvements. Critically analyze your own design. Maybe the database read replicas could become a bottleneck under heavy load. We'd need to monitor that and perhaps add more or explore different caching. Never claim perfection.
Shows humility and critical thinking.
Precisely. Then briefly recap the main design choices, discuss error handling, what happens if a server fails, operational aspects, monitoring, deployment strategies, and maybe future scaling. How would this handle 10x load? If you have time, mention refinements you'd consider. Maybe add a dedicated search service later. It shows you're thinking holistically and about the long term.
That framework seems really solid. Okay, one more practical tool you mentioned that sounds like a superpower, back-of-the-envelope estimation. Why is quickly estimating numbers so important in these interviews?
It's huge because system design is all about dealing with scale. Back of the envelope calculations let you quickly sanity check your design ideas. Is this approach even feasible given the expected load or data size? It's not about getting the exact number, it's about understanding orders of magnitude.
So it helps you rule out bad ideas fast.
Exactly. If the interviewer says 1 billion users and your quick calculation shows your initial database idea would require an impossible amount of storage or handle ridiculous QPS, queries per second, you know immediately you need to rethink it. Maybe sharding is required, maybe a different storage type. It shows you can connect requirements to resource needs.
What kind of numbers or concepts do you need in your mental toolkit for this?
A few key areas, powers of two. Know your data units, KB, MB, GB, TB, TB, and roughly how they relate. 1000 or 1124, it doesn't matter much for estimates. Latency numbers. Have a feel for relative speeds. Memory access equals nanoseconds, super fast. SSD seek is microseconds to low milliseconds. Disk seek, 10 meters, slow. Network round trip in data center, 0.5 meters. Coast-to-coast network round trip, 50, 100 meters, significant. Knowing these helps you choose where to put data in processing. Availability numbers. Understand the nines. 99%, 2 nines, 3.6 days downtime year. 99.9%, 3 nines, 8 hours year. 99.99%, 4 nines, 99.999%, 5 nines equal 5 minutes here. This helps frame discussions about redundancy and cost.
Okay, those relative numbers are key. Any tips for doing the actual math under pressure?
Keep it simple. Round aggressively. 1 million users day. Call it 1M. Average request size 9.7 KB. Call it 10 KB. 860,400 seconds in a day. Round to 100K if it makes math easier. The goal is order of magnitude. Write down assumptions. State clearly what numbers you're using. Okay, assuming 10 MDAU and each user makes 100 requests a day. This lets the interviewer follow and correct you if needed. Label your units. Don't just write 500. Is that 500 millibit? 500 per quaysec. Units prevent confusion. Practice common estimations. Get comfortable estimating QPS, queries per second, peak QPS, often 25x average QPS, storage needs. You jump storage per user, number of users, cache size. You jump percent of hot data, total data size, number of servers needed. You'd be total QPS per server.
So it's a skill you build through practice, using simple math and clear assumptions to quickly gauge feasibility. That really does sound like a superpower.
It really helps guide your design choices. That calculation might tell you, well, we need 50 web servers, or we'll need 10 terabytes of storage in the first year. Those numbers immediately inform your architecture. You can quickly see if a single database instance is plausible, or if you need something distributed like Cassandra or sharded MySQL from the get-go, #tag outro.
Wow. Okay, what a journey. We started right down at the fundamental level, a single request hitting DNS, finding a server.
Yeah, the basics.
Then built up through load balancer, separating tiers, the big SQL versus NoSQL decision, making things resilient with master-slave replication.
And faster with caching, CDNs, and that crucial stateless web tier design.
Plus the asynchronous magic of message queues and the operational necessities of logging, metrics, automation.
And then we really got into the weeds with database scaling sharding, the challenges it brings, and how consistent hashing helps smooth out scaling.
And wrapping it all together, that four-step interview framework. Understand scope, high-level design, deep dive on key components like ID generation or rate limiting, and the all-important wrap-up.
Plus, equipping you with that back-of-the-envelope estimation skill to quickly validate your design choices against the scale requirements.
It feels like we've built a whole system just talking about it.
Yeah.
And the key thing is, this knowledge, it's not just for passing an interview.
Not at all. This is about how you actually design and build robust, scalable, real-world systems. It's about developing that architectural thinking.
That intuition that helps you tackle complex problems, whether you're at a startup or a huge tech company.
So the question for you listening is, now that you have these insights, these building blocks, this framework, how will you approach your next system design challenge, whether it's in an interview or on the job?
What new aha moments are waiting for you as you start connecting these dots yourself? Maybe you'll look at apps you use every day differently now, thinking about how they might handle scale or failure.
It's a continuous learning process.
Absolutely. So our advice is,
Yeah.
practice this. Sketch out designs for systems you know, read engineering blogs from companies talking about their architectures. Keep exploring.
The world of system design is huge and always changing, but these fundamentals will serve you well.
Definitely. Go forth and design amazing things. Thanks for diving deep with us.